So we live in the universe, in our nice little galaxy, on our cozy planet, but the thing is, neither the universe nor the planet and even us should exist. What am I talking about? Alright, a little correction. The fact that we do exist is an exceptionally low probability thing. I'm of course talking about the fine-tuning problem. It's a popular point that for life to appear and survive for billions of years, a lot of factors and parameters had to be just right. For instance, the type of a star we orbit, the distance to the sun, properties of our atmosphere, having a large moon, structure of the solar system, and so on. And that's just the scale of the solar system. Also, the specific location of our system in the galaxy could be better or worse for life. But what about the most fundamental level? The properties of the universe itself. Modern physics describes the universe with a set of parameters. Those parameters have specific values, so there is an opinion that if several, or even just a single parameter had a slightly different value, the entire universe could be completely different. It might not be able to host life or even form stars, planets, and any sort of structure. But there is structure. We exist. And we're able to think about all this. So perhaps all of the parameters have exactly the values to allow us to exist, and that seems quite unlikely. So unlikely, in fact, that some people speculate that someone or something fine-tuned those parameters to allow life to exist. So let's talk about the fine-tuning problem. What exactly are those parameters, what the universe would be like if they were different, and what are the attempts to solve the problem? My name is Andrei, and this is Cosmos Elementary. So what are those parameters and how many of them are there? If you've read anything on the fine-tuning problem, you might know that those parameters are the fundamental physical constants. Martin Rees wrote a book, Just 6 Numbers. As the name implies, the book focuses on 6 fundamental constants. For instance, it's the cosmological constant or the number of spatial dimensions. Standard cosmological model actually includes over 20 parameters, and this paper lists 26. Those are masses of elementary particles, constants that describe fundamental interactions. This list also includes more than 20 parameters: speed of light in the vacuum, gravitational constant, masses of certain particles, and so on. I'll talk about some of them in more detail. I'm going to talk about several examples of those parameters and also about what would happen to the universe if they were to change, and all that based on actual scientific research. It makes sense to begin with fundamental interactions or 4 forces of nature: gravity, electromagnetism, strong nuclear force, which allows atomic nuclei to exist. It holds protons and neutrons together, as well as quarks that make up protons and neutrons. And the weak nuclear force responsible for certain kinds of particle decay. The most basic thing is not even the value of those forces, but just the number of them. We are aware of 4 interactions, but could the universe exist without some of them? The answer is not as obvious as it seems. Well, without any of the first 3, gravity, electromagnetism, and the strong force, the universe would definitely be very different. There would be basically no chemistry, astronomical bodies and structure wouldn't form, and life as we know it wouldn't exist. But the weak force, there are studies that show that in the universe without the weak force, at early stages, neutrons would not decay. They could form deuterium, and in theory, stars could still form out of it. And they could even produce carbon, an element vital for life as we know it. So according to those studies, the universe without one of the fundamental forces, weak force specifically, potentially could still host life. But of course there could be studies with different results, and there are. Some studies claim that even if the weak force were 10 times weaker, long-lived sun-like stars won't exist. So it's not that simple, but we at least can be sure that without the remaining 3 forces, the universe would be completely different. Next, we can compare the strength of gravity against the strength of electromagnetism. Completely without gravity, or even if it were a little weaker, stars, planets, and galaxies wouldn't form. But if gravity were just a tiny bit weaker, but electromagnetism a little stronger, main sequence stars would be much colder, and also massive stars wouldn't go supernova. And that is one of the main sources of lots of heavy elements, especially those that are necessary for life. Again, as we know it. If gravity were a bit stronger, stars would form, but that would require less matter, and consequently they would be much smaller, their lifespan also would be shorter, which is again not very good for life. If the strong force were 50% stronger, the universe would run out of hydrogen at very early stages of its evolution. But in our universe, hydrogen is by far the most abundant element. And if the strong force were 50% weaker, nucleosynthesis, the process that creates heavier elements inside stars, would be way less efficient. There would be no heavy elements and no chemical variety in such a universe. There mostly would be hydrogen. Well, 50% change is kind of drastic, but even the smaller change would lead to the universe not having such important elements as oxygen and carbon. So even not completely removing, just slightly changing the strength of a single fundamental force potentially could render our universe uninhabitable. Life would have nothing to form from. Let's continue. Everything that's made of regular matter, including us, consists of atoms, which consist of protons, neutrons, and electrons. Protons and neutrons in turn consist of quarks. The whole picture, of course, is a bit more complicated. There are gluons, pairs of virtual particles, but now it's not the point. The point is that the particles which everything is made of also have specific properties, and they seem to be fine-tuned. For instance, the mass of particles. And that's apparently true on the most fundamental, currently known level, on the level of quarks. A proton consists of two U quarks, which are also called up quarks, and one d quark known as down quark. The names up and down have nothing to do with actual properties, it's just more convenient to say. Neutrons consist of two down quarks and one up quark. Masses of up and down quarks are not the same. If the mass difference were different, it would affect how stable protons and neutrons could be. Such a universe would be dominated not by protons and neutrons, but rather different variants of quark combinations. And that universe would be perhaps much more simple. If we go one step higher to the level of protons and neutrons, we again could see some apparent fine-tuning. The mass of protons is not equal just to sum of masses of quarks they are made of. As I've said, there is also strong force and all that. Masses of protons and neutrons are close, but not the same. Both are about 1.67 times 10 to the power of minus 27 kilogram, but still neutrons are a tiny bit heavier. Proton mass is this, and neutron mass is this. Very tiny difference, but it's there. In our universe, protons can and do exist outside the nuclei. Actually, a big part of the matter in the universe is in the form of plasma that is made up of protons and electrons. If we flipped the mass difference and made protons a tiny bit more massive than neutrons, protons perhaps would become unstable. Atoms wouldn't form, there would be no chemistry and no life. Also, electron to proton mass ratio looks fine-tuned. Masses of protons and neutrons should be almost the same, with neutrons being just a little bit more massive. Electrons should be much less massive than protons. A proton is 1836 times more massive than an electron. Again, if electrons weren't that light, chemical reactions would work in a different way. There wouldn't be any stable structures such as living cells. There would be no long-lived stable stars. And those are just a few examples concerning properties of particles. Another constant that appears to be fine-tuned is the so-called fine structure constant, which describes the strength of electromagnetic interactions between the elementary particles. Its equation includes several fundamental constants: speed of light in the vacuum, Planck's constant, elementary charge, and electrical constant. The value of the fine structure constant is about 1/137th. It's a dimensionless constant, which means it doesn't have units of measurement assigned to it. The numerical value of protons or electrons' mass would be different depending on what units we chose, but the ratio of their masses will always be 1 to 1836. This value, 1/137th, is known to a very high degree of certainty, but as it is the case for a lot of other constants, we are completely unaware of why it has this specific value. We have no idea. As Richard Feynman once said, it's one of the greatest damn mysteries of physics. 137 is a number that no physicist will ever forget. Some scientists propose to send this number as a message to aliens. The idea is that this way we would be able to show that we have at least some understanding of the laws of the universe. We just should probably send it as a binary code. But what if it had a different value? Not 1/137th, or about 0.007, just a little bit bigger, 0.008, then protons would probably easily bond with each other, and such a universe would have almost no regular hydrogen with a single proton in its nucleus. Without it, stars that are mostly made of regular hydrogen would have a problem, and elements required for life wouldn't form. If fine structure constant were slightly smaller, 0.006, then protons wouldn't be able to bond with neutrons, and that would be problematic for helium, carbon, and so on. Another very important parameter is the cosmological constant, energy density of space or energy of vacuum. I won't go into detail with this one, it is worth a couple of videos on its own. I'll just say that the current value estimates are one of the greatest problems of modern physics. The thing is that theoretical prediction of its value is larger than the one we get from observations. Well, much larger. Depending on the factors taking into account, the difference is 50 to 123 orders of magnitude. Sometimes it is called the worst prediction in modern physics. But even its observed values are intertwined with the fine-tuning problem. A positive value of this constant should lead to the accelerated expansion of the universe, and that's what we currently observe. But if it were just a little bigger, the universe would expand so fast no structure would form. There would be no galaxies, no stars, no planets. And if it were negative, the universe would collapse. At certain values, it would have done it right after the Big Bang. Another thing is the problem of the geometry of space. Sometimes it is said that the universe is balancing on the knife edge. As you might know, in general relativity, bodies are attracted to each other. Not because of some magical force, space is not just emptiness. The space itself is dynamic, and presence of mass distorts space-time, making other bodies follow curved trajectories. Almost everyone should have seen demonstrations like this one. But this is the example of how it works locally, on the scale of stars and planets. But on the biggest scales, the combined mass of all of the matter in the universe has a similar effect on the shape of the universe itself. And the shape depends on how much stuff, stars, planets, gas, dark matter, there is. It is described by such a parameter as critical density. If its value is higher than critical, even if there is just a little more stuff, then the universe has closed geometry. The expansion should eventually stop and the universe collapse. If it is less than critical, then it has open geometry and the universe will expand forever. But if actual density is equal to critical, then the universe is flat. Such a universe is infinite. It will stop expanding only after an infinite amount of time. That sounds confusing though. But what is the problem? So far, all of the measurements tell us that the density is equal or really close to critical. This is not completely certain, and in future some measurements could tell us it might have open or closed geometry. But so far, our best guess that it is flat. This doesn't mean that life wouldn't appear under any other circumstance. If density were a little higher than critical, the universe shouldn't have collapsed too quickly. It would probably last long enough for astronomical bodies to form and life to appear, but if it were substantially higher, then it would collapse too quickly. Still, there is a huge range of possible values, but for some reason the actual value is very close to critical and allows life to exist. Critical density is one of the 6 numbers in Martin Rees's book. Also, there is a number of dimensions. We live in the universe with 3 spatial dimensions and 1 dimension of time, as far as we know. Do I have to even mention that the universe with 2 or 4 spatial dimensions would be completely different? There are actually some studies on the universe with different numbers of spatial and even time dimensions, but most likely life as we know it wouldn't be able to exist in such universes. And that's obviously not all of the parameters we could talk about. For instance, I haven't mentioned the balance of matter and antimatter problem. I had a separate video on that. But still we can see how severe the problem looks. Even by changing a single parameter, we could render the universe uninhabitable. And there are lots of those parameters. How could all of them be just right for life to exist? Seems almost impossible. And yet it doesn't prevent scientists from trying to solve the problem of fine-tuning. Even the question itself, is our universe fine-tuned for life, is kinda confusing. There is no absolute definition of what life is. And also, what life are we talking about? Any life? Intelligent life? Simple or complex? In our universe, carbon life seems to be the most likely option, but what if a universe with a different set of parameters could host life of different biochemistry? We also could underestimate the ability of life, whatever it is, to appear. To all that, we can say that in some of my previous examples, the universe didn't have any complex structures and objects. But it doesn't have to be only two options: structure, no structure. There may be a lot in between. Let's first talk about, let's say, the most controversial solution: the Creator. Our universe seems fine-tuned for life to exist. The chance of that being random is very low, so perhaps someone willingly fine-tuned all of the parameters so that life could exist, and there is some cosmic creator. Creationists love this topic, and it's obvious why this solution might be appealing to many people, though not to scientists. First, this hypothesis can't be tested and also falsified. Even if it's true, it doesn't give us any new knowledge about the universe. It's just a convenient answer. Next, if the Creator were to exist, who or whatever it is, first, why even bother with the constants and fine-tuning? And second, it doesn't give us the ultimate answer, and simply removes it one step further. What are the conditions in the Creator's universe? Who created the Creator and all that? So most scientists don't consider this solution to be satisfactory. Also, we can mention here the simulation hypothesis, which claims that our universe is a computer simulation created by some super advanced civilization. And all of the constants are the way they are because they were programmed to be this way. But this solution has all of the same problems as the previous one. And of course, we shouldn't forget a simple chance. Sure, the probability is super low, but as I've said, even highly unlikely things happen every now and then. If I flipped a coin 3 times and it went heads, tails, heads, would I be able to repeat the same combination after several tries in a reasonable time? Probably. But what if I flipped it not 3, but 100 times? How likely it would be to get the exact same result of 100 flips again? The chance would be unimaginably low, though still not zero. But I did get once this unique set of heads and tails. The specific set is very unlikely to get, but I did get it once. Perhaps our specific set of constant values is just luck. Sure, I won't be able to recreate the same set of 100 flips in 1,000 years, but perhaps once was enough, and our universe is this one time. We got very lucky. And of course, I can't get away from the Anthropic principle. In its last controversial form, it states that we see the universe with a certain set of constants and their values because we can't see it. The different universe wouldn't allow the intelligent observer to appear. The more controversial form was described in the book of John Barrow and Frank Templer, The Anthropic Cosmological Principle. It states that the universe not only has those parameters, it must have them. Universes without intelligent life should not exist. Like it's the purpose of the universe to create life, and even that intelligent observers are required for universes to appear. So yeah, it should be clear why most scientists don't really like this interpretation. If we go back to our Earth and to the question of how many factors had to be present for life to appear and exist for billions of years on our planet, and to the issue of how unlikely it is, there is at least a counter-argument of that there is a lot of planets. Just our galaxy could host 1 trillion planets, and how many galaxies are there? So yeah, life, especially intelligent life, could be rare, but knowing how many planets there are, it's not crazy to think that life could appear somewhere else. Even our galaxy has planets similar to Earth in some respects. But we're talking about the universe, and we have only one of those. It should be obvious what I'm hinting at. The multiverse. I should say that there is no single interpretation of the multiverse. For instance, Max Tegmark describes 4 levels of the multiverse. Now we are interested not in the level 1, where universes are more like just parts of the bigger continuous universe, limited to what we can see due to the speed of light limitations. Those universes should have the same laws of physics. We need the second level multiverse, where universes are isolated bubbles in inflaton field. Here laws of physics could be different. And now it starts looking more like the situation with planets. If there is a huge, perhaps infinite amount of universes, and each has its own laws of physics, we are just lucky to find ourselves in the one with the laws of physics that allow life to exist. Maybe our universe is not even the best one, and there are other better combinations of constants and better conditions for life. But here's the problem. There is no evidence for such a multiverse, and we don't even know how to test it. We also may recall the hypothesis that we could live inside a black hole, and when a new black hole is born, a new universe is born with it. There were even some ideas of how to test it, though so far it's been unsuccessful. Still, this black hole solution is mentioned in some papers on fine-tuning problem. There is also a chance that there is actually no fine-tuning problem. It's just an artifact in data, and it appears because of our limited knowledge. One of the papers I've used as a source for this video has the following comparison. When geocentric model was accepted, so people believed that everything revolved around Earth, they managed to come up with models that at least to some degree fit the observations. Though they had to come up with stuff like epicycles, and they thought it looked like this. Still, it worked for them at the time, but now we know their models were wrong. What if it's the same now? Perhaps new physics, supersymmetry or string theory might solve the fine-tuning problem in future. But even if we don't see the whole picture, even if the problem is not as bad as we might think it is, still a lot of things had to be just right. So that the galaxy like ours, the star like our sun, and the planet like our Earth, and of course we ourselves, could exist.